Welcome to my video, and in this video we'll be looking at the digital to analog converters. Digital to analog converters. Basically, digital to analog conversion is the process of taking a value represented in binary code and converting it into a voltage or current that is proportional to the digital value. It can be considered to be a process that is synonymous to the conversion of binary numbers to decimal numbers. Suppose we have a binary code represented as Bn minus 1, B1 to B0. If we have a binary code represented as Bn all the way to B0, we can obtain its decimal equivalent as follows. So the decimal equivalent will be given by Bn multiplied by 2 power n plus Bn minus 1 multiplied by 2 power n minus 1 plus B1 multiplied by 2 power 1 plus B0 multiplied by 2 power 0. From this conversion, we notice two things. One, we need to observe the positional value of each bit and therefore multiply every bit with its positional value. And this is what we call weighting in the conversion. Each of the bits is multiplied by a weighting factor. And then number two, we sum all the weighted values of the individual bits. So we sum, we obtain the aggregated value of each of the weighted bits. And therefore, we need to perform summing. And therefore, the simplest digital to analog converter can be considered to be a device that is able to carry out the weighting of each of the individual bits, and number two, carry out the summation of the weighted values so as to obtain the aggregated value of the resulting value. We have a number of digital to analog converters developed on the same principle. The first such a converter is what we call the weighted resistor, DAC. Weighted resistor, digital to analog converter. In the weighted resistor, digital to analog converter, resistors are weighted such that the resistors are inversely proportional to the numerical significance of the corresponding numerical digits. And therefore, we maintain an inverse relationship between the resistor values that we have and the numerical digits in the digital code. The operation of the converter depends on successive resistances being related by a factor of 2 and does not depend on the absolute values of the resistors. In other words, we maintain the resistor values such that they are related by a factor of 2, and we are not interested in the actual values of the resistors in the fabrication of the DAC. Then finally, we use the operational amplifier as a summing amplifier, which produces a weighted sum of the input voltages. And therefore, weighting will be done using resistors, and the operational amplifier as a summing amplifier will be used to carry out the weighting of the input voltages. For example, we can have a 4-bit weighted resistor converter of a similar configuration as follows. So this is our operational amplifier in its inverting mode. The resistors, they are a ratio of 1:2 from one resistor to another. So if we start with R, we have 2R, 4R, and 8R. Said that the resistors bear an inverse relationship in terms of the bit contribution. So we expect then this is the most significant bit and this is the least significant bit. If you consider these bits to be A, B, C, and D, then we have a feedback resistor. And our output is going to be obtained as our output VO. Then the most significant bits, that is the bits A, B, C, D, can be written as D, C, B, A, D being the most significant bit and A being the least significant bit. They can take values of 0 or 1. So you can have a situation where all of them are 1, 1, 1, 1, all the way up to when all of them are 0, 0, 0. For the value 1, we use a reference voltage, which for most of the digital systems, we can use 5 volts, or sometimes we use 3.3 volts. Then for bit 0, this is 0 potential, or we ground the bit. From this, we notice that then the current that will be moving in the forward direction due to each of the bits will depend on the bit value multiplied by the reference voltage of the ground and then divided by the resistance. And then on the forward feedback path, we have the output divided by the resistance R. We can write, therefore, the currents as follows. Current that's moving from the feedback direction is V out over R, which will be the negative of the currents, because if you take Kirchhoff's current law at this node, the currents that leave the node is 0, and all the currents are getting into the node. Then we can write this as the reference voltage multiplied by D over R plus the reference voltage multiplied by C over 2R plus the reference voltage multiplied by B over 4R plus A over 8R. If we multiply both sides by R, we notice then our output, V out, will be equal to negative reference voltage into D plus C over 2 plus B over 4 plus A over 8. And this becomes the analog equivalent of the digital called DCBA, considering that the reference voltage VREF can either be 5 volts or 3 volts, depending on the digital system in question. And this is the operation of the weighted resistor DAC in its conversion of digital signals into analog signals. We notice that whenever we want to increase the number of bits for our DAC, and every time we've got to maintain a ratio of 1:2 from one resistor to another, or from one bit to another, then the value of the resistors will be increasing, and at such a point, then the ratio between the lowest resistor and the highest resistor becomes very high. For example, if we want an 8-bit DAC, then we'd have 16R, 32R, 64R, and 128R. That means the ratio of the lowest to the highest resistor in an 8-bit weighted resistor DAC will be R is to 128R, which is 1:128. And this ratio is very high. To avoid this, we modify the weighted resistor DAC to form the second type of the DAC called the modified weighted resistor DAC. Modified weighted resistor DAC. The modification is carried out so as to accommodate the large number of bits without a consequent spread in the resistor values. So we want to increase the number of bits, but at the same time, we control the spread in the resistor values. We will illustrate this with an 8-bit modified weighted resistor DAC, which would look like this. So we have the 8 resistors, but grouped into 2 sets of 4 resistors. The second set is connected through an additional resistor, and then the 2 of them goes as the input to the negative terminal of the operational amplifier. So these resistors maintain the same ratios, R, 2R, 4R, and 8R. We also maintain the same ratio, R, 2R, 4R, and 8R. So this resistor is also R. And then we connect the second set of the 4 resistors to a resistor small r, and these are our 8 bits. So this will be the least significant bit. We can call it bit B0, B1, B2, B3, B4, B5, B6, and B7, where this is the most significant bit and this is the least significant bit. And this is our modified resistor DAC. So the 2 resistor sets, they bear the same ratio, R to 8R, but the second resistor set has another resistor, small r, connected to it, and then all of them connected into the negative input terminal of the operational amplifier, and our output is taken at that stage. The only challenge in this is the determination of the resistor small r, the value of the resistor small r, that would ensure that our weighted resistor DAC with the modification maintains a similar ratio to the unmodified weighted resistor DAC. We can analyze the operation of this DAC and determine the value of the resistor small r as follows. If we let bit 3 to be 1 and all the other bits to be 0, and we analyze the second stage of the DAC, then we can have the following circuit. This is small r. This is the second stage that we have introduced into our DAC. This is bit 0, bit 1, bit 2, and bit 3. If bit 1 is a 1, that means we connect this to a voltage source, and then we ground all these other bits so that their values are 0. Then we know that the current contribution between bit 7 and bit 3 would bear a ratio of 1:16 if the DAC is unmodified. So the introduction of the resistor small r should not interfere with the ratio of the currents between the most significant bit and all the other bits. So for bit 7, we know the current contribution will be the reference voltage divided by R. For bit 3, bit B3, the ratio or the current contribution to that resistor should be the reference voltage divided by 16R. And then you can see then the ratio between the current due to the most significant bit and bit 3 is 1:1/16. Now, with that in mind, then we can consider the current contribution due to bit 3 alone in our reduced circuit. You notice that resistor 2R, 4R, and 8R are in parallel because they share this point, and also because they are grounded, they share a common point, and therefore these resistors can be considered to be resistors in parallel. The positive terminal of the operational amplifier is grounded, and therefore the negative terminal would also acquire a ground, a virtual ground, and therefore we can also consider the parallel combination of 2R to 8R in parallel with resistor small r, because they share this point and their other ends are also grounded, which means in terms of potential, these 2 points are the same, and therefore this resistor network and a small resistor R then can be considered to be in parallel. We can draw the equivalent circuit having considered the parallel combination of these three as 1/R total to be equal to 1/2R plus 1/4R plus 1/8R, from which we get this to be, that is LCM is 8R, so we'll get 4 plus 2 plus 1, and this is 7/8R. This is our total resistance, 1/R total. That means the total resistance then is 8R/7, which means we can have a modified or reduced circuit with a resistor 8R/7 in parallel with small r, and then in series with our R as follows. So our network can be modified as follows. This is our network. This is our network. So we have a reference voltage here, our resistor R, and then 8R over 7 and R are in parallel. Then we can consider the total resistance of the network. We have 8R over 7 in parallel with R, and then plus R to be our total resistance, in the network, which will give us 8R over 7 multiplied by R over 8R over 7 plus R, which will give us 8R over 8R plus 7R plus R. That's our total resistance, which will give us 8R plus 7R. Then the product here will give us, this will give us 8R squared plus then 15RR. This is our total resistance in the network. Our total current in the network will be the reference voltage, Vref, divided by R total, which will be equal to 8R plus 7R into the reference voltage divided by 8R squared plus 15RR. So this is the total current, I total. The current that gets into the operational amplifier is the total current subdivided into 2 by the current divider theorem, as the current due to that resistor, which is the current contribution due to bit 3 that gets into the operational amplifier, which we're interested in. And therefore, you can say the current due to the bit 3 that gets into the operational amplifier will be equal to, then by current divider theorem, we interchange the resistances to 8R over 7 over 8R over 7 plus R multiplied by the total resistance, I total, which will be equal to 8R over 8R plus 7R multiplied by 8R plus 7R multiplied by the reference voltage divided by 8R squared plus 15R small r. You notice that these terms will cancel out, and you will get this to be 8R over 8R squared plus 15RR multiplied by the reference voltage. And this is the current contribution due to bit B3. We noted that the current contribution due to bit B3 is also given by the Vref over 16R, and therefore we can equate the two and state that the current that we have obtained so far is the same as the reference voltage divided by 16R. The reference, we notice then this can cancel out. If we cross multiply, we will get 128R squared will be equal to 8R squared plus 15RR, from which we'll get 120R squared, R squared will be equal to 15RR, and we divide both sides by 15 capital R, we'll notice that our R will be equal to 8 capital R. And this is the value of the resistor that we need to introduce into the second set of the resistors so as to obtain the modified weighted resistor DAC. And therefore, this resistor will be equal to 8R. Otherwise, the rest of the operation of the modified weighted resistor will be similar to that of the weighted resistor DAC previously discussed. Lastly, number 3, we have what we call the R2R ladder network. DAC. We have the R2R ladder network DAC. The R2R ladder network uses resistors of only two sizes, R and 2R. This array requires twice as many resistors for the same number of input bits as the weighted resistor array. In other words, we need twice as many resistors in the R2R network as compared to the weighted resistor DAC. The bits are weighted by providing paths for current division with consequent succession attenuation of bits of lower significance. And then the operational amplifier is also used to sum the current contributions of each of the individual bits. An example of a 4-bit R2R ladder network is as shown below. A 4-bit R2R ladder network is as shown below. We have the 2R resistors in parallel. And then the R resistors in series. So these resistors are value R, 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 whereas these are 2R. Then we connect these zero switches. We can have the most significant or the least significant bit connected to the source, whereas all the other bits are grounded. So this is our reference voltage. This is 2R. This is an example of a 4-bit R2R ladder network, where this is the least significant bit, and this is the most significant bit. We can call this bit A, bit B, bit C, and bit D. So A is the least significant bit, and D is the most significant bit. Let's assess the current contribution due to the least significant bit A. With all the other bits grounded, then that would mean that the current would be flowing through the least significant bit circuitry. Then when it gets to this junction, a portion of it will flow in this direction and a portion of it in this direction. So we need to assess the equivalent resistance from this point towards the right. If you look at this resistor 2R, if the positive input terminal is grounded, that means the negative input terminal also acquires a ground. Resistor 2R, 2R, they share this point and their other ends are grounded. That means this resistor and this resistor are in parallel. The parallel combination of these two will give us the product of a sum, which is 2R multiplied by 2R over the summation, which is 4R. And this automatically will give us R as the resultant resistor. Then the equivalent resistor R is in series with R in series. That means again the total resistance will be R plus R, which is 2R in parallel with this R. Again, 2R and 2R in parallel to give us R, R in series with R to give us 2R, 2R in parallel with 2R to give us R, and then in series with R. And therefore, from this point onwards, the resistance that we see is 2R. We can modify the circuitry as follows. So we have the 2R. We can shift now our source to this point, our reference voltage, because the current is only flowing through this loop. Can bring the reference voltage here. This is 2R, this is 2R. And then from this point onwards to the right, we also see 2R. Therefore, the resistor at this point is also 2R, and this is our equivalent network. So this is 2R. The total current that flows at this point, our I total, comes and subdivides into two parts at this point. And you notice that these 2R and these 2R are in parallel because they share this point and also they share the common ground. That means from these two resistances, 2R and 2R in parallel, we'll get the total resistance to be R. That R in series with 2R will give us our total resistance to be 3R. With our total resistance being 3R, then our total current, I total, is going to be the reference voltage divided by the total resistance, which is 3R. And this is our total resistance, our total current in the network. That current, when it comes to this point, subdivides into half-half because these two resistors are equal, and half of it, half of the I total flows in that direction, and half of the I total flows in this direction. So up to this point, we will have I total divided by 2, and up to this point, we have I total divided by 2. And this is the current due to the least significant bit A. We would wish to get the current that gets to this point, which is the current contribution due to the least significant bit that gets to the operational amplifier network. And this is the current IA that we're interested in. Notice that the same current, when it comes to this point, again, we divide half, since the total resistance seen from this point is 2R and at this point is 2R. And therefore, at this point, divides into I total over 4. When it comes to this point, the same current subdivides at these 2 points and to get I total over 8. And lastly, at this point, this being 2R and 2R subdivides into I total over 16. And therefore, the current contribution due to bit A, IA, will be a 16th of I total, which is a 16th of Vref over 3R. And this is the current contribution due to the least significant bit. If the opposite was to happen such that the most significant bit is connected to 1 and all the other bits are grounded, you notice then the current will be emerging from this point, subdivides to the left and to the right. It means it's the same total current, but subdivides at this point half-half. That means the current due to the most significant bit will be a half of the total current. And therefore, the current contribution due to bit D is going to be a half of Vref divided by 3R. Following the same analysis, then the current contribution to bit C and B will be a quarter and an eighth of the total current respectively, from which then we can write the equivalent current as follows. Our output voltage divided by the reference voltage will be equal to, on the feedback path, we have a reference resistor. The current in the feedback path will be V out divided by RF. You can write this as RF, which will be equal to negative D over 2. You notice the current contribution due to bit D is a half, plus C over 4. Current contribution due to the second most significant bit is a quarter, plus B over 8, plus A over 16. All these multiplied by the reference voltage divided by 3R. Remember, the current contribution due to the most significant bit, or the total current in the network, is Vref over 3R, and therefore a half of that due to the most significant bit and a 16th of that due to the least significant bit. From which then we can write our output voltage will be equal to negative Vref over 3R into D over 2 plus C over 4 plus B over 8 plus A over 16 multiplied by the reference resistance RF. And this becomes the output analog voltage equivalent to the digital bits D, C, D, A, with the D being the most significant bit and A the least significant bit. And that is the operation, the construction and operation of the R2R ladder network DAC. And that brings us to the end of our discussion of the digital to analog converters. We've discussed the weighted resistor DAC, the modified resistor DAC, and the R2R ladder network DAC. Otherwise, thank you so much for watching this video. In my next video, we shall be discussing the analog to digital converters. Thank you so much.